Hello and welcome everyone to this short paper session on text and communication. My name is El-Assady and I will be chairing this session. Today we have 7 excellent papers that will be presented. We will first watch the pre-recorded videos, which will be followed by live Q&A. So without further ado, let's start with the first talk by Vidya, and the paper is entitled Sentifiers, Interpreting Vague Intent Modifiers in Visual Analysis Using Word Co-occurrence and Sentiment Analysis. Take it away.
I'm delighted to present our work on Sentifiers. This research was done with my colleague Arathi Kumar at Tableau. The main goal of natural language systems is to understand user intent so that systems can respond sensibly. However, with the complexities of language, intent is not always easy to convey. It is even harder for human-computer conversations as nonverbal cues are missing and information is underspecified. Search queries consist of keywords and terms called modifiers that imply intent. Consider the utterance, "Find me the best coffee shops near Palo Alto." The modifier, near Palo Alto, specifies an intent of finding coffee shops in the vicinity of Palo Alto. These modifiers can be interpreted along a spectrum, as seen with examples on the slide, ranging from more precise and concrete ones when used with an item or object, to more vague, where the interpretation often depends on the context of the information and the object being referenced. And it turns out that people do use vague modifiers when interacting with these natural language systems. The table here shows an edited view of the top modifiers. Natural language interfaces for visual analysis need to understand intent and handle modifiers. For example, Ask Data is a system that handles numerical vague concepts such as cheap and expensive by inferring a numerical range. More recently, Hurst et al. Explored visualization responses to singular and plural superlatives and numerical graded adjectives based on the shape of the data distributions. We extend this work to better understand how we can interpret more subjective modifiers. In this work, we explore more fuzzy subjective modifiers in a visual analysis context, employing word co-occurrence and sentiment analysis to determine how to interpret them. Now let's walk through a quick overview of the Sentifiers system. The system is based on a web-based architecture with the input query processed by an ANTLR parser with a grammar. A part-of-speech tagger identifies the modifier adjectives and their referring attributes. Sentifiers then computes the semantic relatedness between the modifier and the numerical data attributes using a co-occurrence measure. A data manager executes queries to retrieve data. Sentiment polarities are computed to determine numerical ranges to be associated with the modifier. A visualization result is then generated showing the widgets and filters in play. Now let's look at a demo of the system to see how all these components come together. This is a data set of earthquakes in the US. I start by typing, "Where is it safer?" Sentifiers interprets the modifier safer as a positive sentiment and the numerical attribute magnitude as a negative sentiment, showing a bottom range. Clicking on the range in the text response displays a widget that can be used to refine the value. I now type, "How about the dangerous places?" The modifier dangerous and magnitude both have negative polarities showing a top range. I change the value to 5 and the visualization updates. The system uses the Richter scale for determining ranges from the Wolfram alpha corpus associated with the dataset. Now let's look at a dataset of health and wealth of nations. I type, "Which countries are booming?" The modifier booming, along with its closest co-occurring attributes, income per capita and life expectancy, have positive sentiments. I adjust the slider for income per capita and notice the visualization updating. Similarly with life expectancy. I add an additional attribute, population. I next type, how about the struggling ones? Struggling has a negative sentiment and bottom ranges are shown. Refinement includes adding attributes as well as removing any attributes that a user does not want to associate with the modifier. Going into some detail about the individual techniques employed in the system, consider the utterance, where are the safe places to live? We employ a part-of-speech tagger with the parsing process to identify adjectives that are typically modifiers. The system can distinguish complex gradable adjectives like safe, as you can see here in this example, from other numerical gradable adjectives like most and less by inspecting if the adjectives have numerical semantics that are comparative or superlative in nature. The next step in associating the vague modifier with the set of numerical filters on the attributes in order to generate a visualization response. We determine the semantic relatedness of the modifier with a set of numerical attributes in the dataset using Google Ngrams. We compute a pointwise mutual information score to quantify the probability that a modifier co-occurs with an attribute. In this example shown here, the PMI values for the modifier struggling is shown with each of the three numerical attributes in the dataset, income, life expectancy, and population in the Google Ngram corpus. Higher PMI scores indicate a high co-occurrence of the modifier and the attribute terms. Once the modifier is semantically associated with the co-occurring numerical attributes, we need to determine a reasonable numerical filter range to associate with the modifier. Sentiment polarity is a linguistic technique that uses positive and negative lexicons to determine the polarity of a phrase. We compute sentiment polarities of the modifier and the attributes using their individual sentiments and applying the following combinatorial logic shown here. We treat neutral sentiment similar to positive sentiment, as neutral text tends to be near the positive boundary of a positive-negative binary classifier. Here is an example showing normalized sentiment scores for a modifier and attribute combination. Modifier safe has a positive sentiment and earthquake magnitude has a negative sentiment, resulting in a bottom range on magnitude determined by the Richter scale from Wolfram alpha. After the system executes the query, the system interpretation is expressed in the form of interactive text inspired by Brett Victor's work. These interactions help the user understand the provenance of how the modifiers were interpreted and can be refined by the user if needed. We conducted a user study with 10 participants to collect qualitative feedback and identify system limitations. Overall, participants were impressed with the ability of the system to understand their queries and used several modifiers. The text feedback provided in Sentifiers was found to be helpful to understand system behavior and correct the system's response. Future work to address the system limitations include handling more complex queries, supporting customization, and addressing biases. Thanks for listening. Here's a link to the paper along with contact information if you have any questions or comments.
Thanks, Vidya. That's really impressive work. So for everyone watching live, feel free to add questions in Discord or on YouTube. And let me start with a question. So you described how you would extract the intent from a single query. And I was wondering how that could be extended later on, maybe to actually take in the whole interaction history or history of queries that users have inputted. So have you thought about that?
Yeah, so currently the system can keep track of interaction history for a single user for a particular session. It is pretty straightforward to store that interaction information and be able to at least provide some customization for a user or a corpus of users who share similar preferences.
Mm-hmm. And have you noticed any difference between seeing the users interact using text-based systems versus actually guessing the interaction by their queries, or have you thought about doing that in a visual manner other than just using the text input?
So right now the system is a mixed initiative type of interaction. So users can use text and widgets. What I've noticed with this system and just previous work, there's a certain degree of expressiveness that a user can express through intent, through text, like these subjective terms. But in terms of modifying and repairing the intent, users tend to find it to be less tedious if they actually use widgets through direct manipulation, even though they could repair stuff through linguistic expression.
Yeah.
Yep.
Great, thank you so much. All right, so we'll transition to our next talk, which will be given by Alex Ahmed, and the paper is entitled Data Visualization for Transgender Voice Training. Take it away.
Hello all, my name is Alex Ahmed, and I'm here to present work conducted with Dr. Michelle Borkin. Our paper is titled Data Visualization for Transgender Voice Training. I'll begin by taking a minute to explain what voice training is. When we talk about transgender voice, we are talking in general about a transgender person's experience of their speaking voice. These experiences vary widely. Some choose to or are able to pursue formalized voice training to change the way their voices sound in some way. Others don't. Those who do pursue it could be aiming for a higher or lower pitch, a more consistent or variable pitch. It could also be the more complex task of changing the way your speaking voice resonates. It can be very distressing to feel like your voice doesn't represent you, or that it opens you up to being identified as transgender against your will and potentially assaulted. None of these are universal experiences, but this is an issue that folks may come up against in their day-to-day life, regardless of whether they choose to pursue voice training or not. Over half of transgender women, about 62%, are interested in voice training or have done it. Professional therapists and specialists are an option for those who can afford or access them, but there are also a number of online resources, YouTube, forums, and mobile apps that all aim to support trans people in working on their voices. I'll now review related work in visualization that will help situate our project in relation to ongoing developments in the field. One of the guiding frameworks for our project was D'Ignazio and Klein's feminist data visualization. Their work calls researchers and designers to rethink binaries, embrace pluralism, examine power, consider context, legitimize embodiment, and to make labor visible. A full review of each of these points is outside the scope of this presentation, but in short, the authors argue that designers should consider the social and cultural context in which artifacts are created and how they might be received. We can use these principles to critically examine existing speech visualization tools. Consider this visualization, which takes a user's voice recording as an input to detect whether it is abnormal with respect to its pitch, frequency variation, and other metrics, relative to a sample of healthy men or women. Our objective here is not to disparage this research, but rather to ask, who defines these terms? Healthy and abnormal. And what are the consequences both at the user experience level and at the societal level? This visualization design may force the user to make an impossible choice if they don't identify as a man or a woman. By rethinking binaries and legitimizing embodiment, we might imagine a solution that provides more expansive options for a user's gender selection, or to eliminate the requirement to select one's gender altogether. This system may also make users feel stigmatized if their voice is marked in red and as abnormal. Examining power and context helps us recognize that disabled and transgender individuals are already stigmatized and othered in our society, and so this system may reinforce existing power imbalances rather than aspiring to empowerment, that is, to improve upon or address a social inequality. These issues are also present in existing voice training apps for transgender people. In the pictured apps, users read a passage and then receive a readout of their voice's average pitch in comparison to preset gender categories. VoiceUp, the app on the left, presents the user with a series of percentages without any contextual information. Some users may understand this output as 70% of their speech was in the male pitch range, but this design choice evokes harmful tropes and slurs about trans people being partly men or partly women, which is reinforced by the use of a donut chart. The design decision to render gender categories as discrete emphasizes their construction as separate categories that do not permit fluidity, mixing, or crossing. I'll now go into our design process, in which we attempted to create a speech visualization for trans people that aspires to empowerment, that opens up more expansive options for users to explore and affirm their voice in relation to their gender identity. To begin, we interviewed 10 transgender people about their experiences with voice and technology, and then clustered those quotes into an affinity diagram to explore major and recurring themes. In the interest of time, I'll just go over a couple of quotes that I think are particularly relevant, but please see the full paper for details. I'll refer to participants using pseudonyms. Our interviews revealed that an overemphasis on analytics may not be useful. Instead, our app could encourage reflection and self-determination. One solution could be to ask the question, what do you want to sound like? By framing it as a question, one participant, Miriam, suggested that the goal interaction could be co-constructed between the user and the system. It could be like a dialogue rather than the app dictating what you should or should not be doing. As part of this design work, I also conducted a task abstraction. Here, I distilled the required goals of the user into a common taxonomy, which you can see underlined and capitalized in each box. Our affinity diagram and task analysis suggested that a successful voice training system should include some voice training functionality, summarization of voice data, user-defined goal setting, that is a pitch target that aligns with the user's sense of self or identity, a way for users to reflect on their data and determine what they want their goal to be, and a comparison of the user's voice performance in relation to their goals over time. And so we design an exercise where users freely respond to a randomly selected question asked by an animated cartoon character. While the user is responding, the app records and calculates their voice's pitch. We created a number of exploratory sketches to figure out how we wanted the user's pitch to be visualized. Knowing that we needed to encode the distance between the user's own pitch and their goal, we played with vertical position, angle on the arc, and skeuomorphic visualizations that represent real-world objects, here a piano and a gauge. We then explored the usability of these designs through several rounds of user testing. A digital survey was created in Google Forms and distributed to 2 online communities of transgender people interested in voice training. A total of 20 individuals responded. Some respondents to the survey described the gauge visualization as unclear. One participant perceived it as a bell curve rather than a gauge and called it unusual. Another respondent felt that it would be better if they could visualize how far they are to their goal, and that the gauge visualization doesn't fulfill that purpose. As a result of this feedback, we altered the visualization to encode the user's pitch relative to the goal as a vertical position, rather than as an angle on the arc. In our final design, we emphasize user control and affirmation throughout the app, using a text-based feedback and encouragement text, and the inclusion of the user's own goal. So rather than base our feedback in gendered language, such as "your voice sounds male," we center the user's own choices. We see our current design as fulfilling 3 out of 5 of our original design requirements, but more development and user testing is required for us to meet the rest. In the meantime, we value any feedback or questions. Thank you very much for listening.
Thank you so much, Alex. That was really great work. So we have people typing, and I hope some questions are coming in. But for me, I will start with a comment, and I was really liking the pitch that you had with like using the data feminism principles, and also like using visualization for personal empowerment and personalizing visualization design. And I really like also in the paper that you wrote that you want to use that for enhancing self-image and self-understanding. So I was wondering, it's not really a question, but where are you going from there? So what are your future plans? based on that work?
Yeah, so after we created the prototype that I presented in this talk, we gave it to users to test out and try, and then we interviewed them about their experiences. So we saw a lot of variability in how people use it in their day-to-day life, and those are really interesting to draw out because transgender folks are, you know, a really heterogeneous group, come from like all racial, class, cultural backgrounds, and that affected how they used it. I go into that more in my thesis, which I can link in the Discord.
Yeah, perfect. Thank you so much.
You're welcome.
Yeah, so I think some people are typing, so maybe there are more questions coming in on Discord. I think that's a really lovely discussion to be had.
Yeah, sure. Thanks, everyone.
Okay, our next talk is by Alejandro, and he will present GlassViz, visualizing automatically extracted entry points for exploring scientific corpora and problem-driven visualization research. Take it away.
So hello, and thanks for the introduction. My name is Alejandro Benito-Santos. I'm a research assistant and PhD candidate at the University of Salamanca in Spain. And I'm presenting my work, GlassViz, visualizing automatically extracted entry points for exploring scientific corpora in problem-driven visualization research. Okay, so problem-driven visualization research is a kind of interdisciplinary practice in which domain and visualization experts collaborate together to solve specific problems in an area of knowledge, such as bioinformatics, digital humanities, or computer security. So it is common that at the beginning of these studies, the researchers go to the literature trying to find existing visualization techniques that can be imported into their own domains in what is called as methodology transfer. So the way they usually go about this is that they employ terms that typically co-occur with concepts defining their domain problems. So, but there is a problem with this approach, is that when using these intermediate terms, they will retrieve many documents that they will have to browse manually in a time-consuming task. So we wondered if there was a better way to support this task, and if we could make these researchers find interesting techniques in a better manner, or in a faster manner. So we relied on a technique that is called literature-based discovery. So literature-based discovery was coined in the 1980s by Don Swanson, who was an information scientist, and he discovered a link between fish oil and Raynaud's disease, which is a circulatory disorder. So for this, he used something that was later called as the ABC model, that works on a simple syllogism. So the way it works is that if one can find an A concept that is associated with a B concept in a body of literature, and that B concept can be found with a C concept in another different body of literature, then there is a connection between the A concept and the C concept that is defined by the B concept. So there are current efforts to apply this model to other domains different from the medical domain, and they mainly work on the idea of word embeddings and distributional similarity. Distributional similarity refers to the idea that two words are considered similar if they tend to appear in the same context. This is surrounded by the same words. So to illustrate this concept, imagine a problem that appears in a body of literature that also occurs with other concepts. And in turn, we have two techniques in a different body of literature that may be potentially interesting for solving this problem. So following this network of co-occurrences, then it is easy to see that technique 2 in this case is more fit to solve our problem according to what can be found in the literature. So we augmented existing models with this idea of high-order co-occurrence to find connections between different parts of the literature. So for this, to provide an implementation of this model, we relied on embeddings that were built from author-assigned keywords. And in particular, we took these author-assigned keywords from two research paper collections. One is a collection of papers on visualization for the digital humanities that was built by us in a previous study. And the other one is VIS data that you probably know, and it contains visualization papers that have been presented at this conference in previous years. So very quickly, in order to get our embeddings, we firstly compressed the input data, so with tokenization and stemming. Then we divided the tokens depending on whether they appeared on the VIS48 collection or on the VIS collection exclusively, or in both. So we calculated a positive point-wise mutual information matrix that in turn was factorized using SVD, so singular value decomposition. Just for this presentation, these vectors were projected in the bidimensional space using a UMAP. So you can see more or less how they are distributed. And we are interested in analyzing the neighborhoods that connect A concepts to C concepts in the shortest possible distance. For this, we coined the concept of quality neighborhoods. So we removed directly the neighborhoods that did not contain C concepts. Then we measured the distance from the A concept originating the neighborhood to their closest C concept in the neighborhood. And we only took those that fell within the first quartile of the distribution. And finally, we merged these neighborhoods when they have coincident nodes. Since we didn't want to compare the neighborhoods, so we didn't use this body plot, but rather we created a complete distance graph and created a minimum spanning tree. So we removed the edges that were not on shortest paths. And so we created a proof of concept prototype that depicts this idea. And here you can see how in the main view these entry points to the dataset are depicted. So they link together different terms that show high distributional similarities. So on the right, you can see a rank frequency list with the contexts that the terms in the entry point typically co-occur with. And at the bottom, we can see a list of documents also sorted by rank, which also give the user an order, a reading order in which she can start exploring the collection. Okay, so that was it. Thank you very much, and I'm ready to take your questions.
Thanks, Alejandro. It's really great work. I really like that people picked up this idea of methodology transfer and actually got the corpus of this for the H paper to analyze. Like, thank you for that. So we still have some people typing, but let me start by adding a question about how people would interact with that to like add their own domain knowledge. So if I, for example, I'm an expert in a particular field and I want to add concept relations because I know these kind of concepts are related, or that might not be presented in the data, but I know these relations exist. How do you suggest we can add these in the tool that you have?
This is a very nice question. Actually, I've been trying lately to incorporate other problem-driven visualization domains, right? Like VIS, so I've been experimenting with data that I'm collecting from several other workshops like VSEC, etc. And I think that there are many opportunities to perform or to employ direct manipulation techniques that you know very well, and that I think that would make its exploration very personal, which is the main aim, right? Because each researcher has his own or her own particular research context, and these techniques would be of much help, I think.
Yeah. All right. Thank you. I'm looking forward to see what you do with the other corpora. Thanks very much.
Thank you very much.
Right. So now let's move on to our next paper by Sahaj, and the paper is entitled "Knowing What to Look For: A Fact, Evidence, Reasoning Framework for Decoding Communication, Communicative Visualization." Go ahead.
Hi everyone, I'm Sahaj Vaidya, a PhD student at New Jersey Institute of Technology, and this work is in collaboration with my advisor, Professor Aritra Dasgupta. In this paper, we talk about decoding communicative visualizations. But first, let me decode this long paper title for you. As seen in the chart here, you get what you see. The amount of information represented is simple. It just talks about the number of flu cases for one country. Whereas for this chart, you still get what you see, but you need to reason more, though the amount of information presented is similar to previous. For this bar chart, the information shown increases, but as you probably have realized, with minimal effort, you can understand what the chart wants to convey. But for this line chart, the information represented is more complex. It requires comparison of multiple time series. So a question which pops up in our mind here is that why do we need to characterize these differences? The reason is that it helps us to understand how the decoding process works and use this knowledge to construct better communicative charts. We propose a quadrant-based classification and adopt the concept of faceted search for high-level classification of facts. Let me show a few examples to explain the difference between these facts. Unifaceted facts, like the line chart and the scatter plot shown here, are those which depict one dimension corresponding to a given measure in a visualization. Whereas multifaceted facts, like the bar chart and the time series, are those which depict more than one dimension or more than one measure along different scale in a visualization. This process of gathering evidence and finding fact is highly dependent on the nature of fact and evidence. Based on this, we derive two broad categories of evidence. Descriptive evidence, as seen in the figure, can be considered as a minimal amount of evidence that can be used to substantiate a fact, whereas inferential evidence requires the user to put together multiple pieces of information to derive the fact. Hence, inferential evidence necessitates an added amount of reasoning. Having given this classification scheme, a concern here is that what exactly do we look for when we come across a chart? So while terms like message or insights are often used for this purpose, they have unclear definitions and are loosely connected to downstream perceptual tasks and cognitive processes. As a solution to this issue, we propose a fact-evidence reasoning framework to understand the key takeaway of a scientific visualization. This framework, as seen in the figure, provides additional input stages of understanding fact and gathering evidence, which triggers the process of reading charts. To instantiate this framework, we collected charts from 3 scientific domains. These include climate science, healthcare, and energy. For collection of charts, we consulted various domain scientists who pointed us to different research publications, from which we extracted around 500 charts along with their captions to derive the framework. This framework helps us to identify certain important trends in our collection. On moving along the y-axis from unifaceted to multifaceted, the complexity of retrieval-based tasks increases. The reasoning, as you probably have noticed, is that the number of dimensions and measures increase, so the amount of information to be extracted also increases. Whereas on moving along the x-axis from descriptive to inferential, the complexity of reasoning-based tasks increase. Why so? The reason is because the user has to put together a lot of time and effort for decoding the inferential evidence. This quadrant-based classification helped us to identify certain important factors in chart collection. One of them is that mental computation can be easily mitigated with the help of visual cues. Another factor which plays an important role is the presence of textual explanation. When user encounters a visualization, presence of some kind of textual explanation guides their attention towards what needs to be seen and thus saves them some extra effort. A third obstacle is that of missing information. This can lead to potential incorrect or incomplete derivation of fact. So how can we leverage this framework? This framework implies that there are certain design and informational requirements of visualizations, essentially a type of metadata behind the visualizations. Different approaches focus on different variances in communication. Hence, the goal of this framework is to characterize the cognitive processes invoked from within a visualization and how these processes support the communication of data from visualization to a viewer. So, to wrap up, I would say that the goal of this framework is to serve the dual purpose of input and output-oriented reasoning from the perspectives of a visualization designer and a consumer. Please feel free to put down any questions that you'd have. Thank you.
Thank you so much, Sahaj. This is very timely work, and I think in these times where we see a lot of miscommunication and misinformation, that's really, really important. We have a couple of questions that came in on Discord and YouTube. So let me start with the first one. Can the charts having inferential evidence include descriptive evidence as well?
Yes, actually descriptive and inferential, the categories of evidence are derived from the descriptive and inferential statistics. So descriptive evidence is basically a minimal amount of evidence. The user does not need to put a lot of effort to derive that kind of evidence. Whereas for inferential, you have to draw inference based on the semantics of the visualization. Hence, inferential evidence also includes the descriptive evidence as well.
Yeah, perfect. So there is one more question on Discord, and I think we can move on the discussion there because we need to move on to our next talk. Thank you so much, Sahaj.
Thank you.
Our next talk is MeetQ supporting online meeting experiences, and it's given by Marius.
Hello everyone, I'm Marius Konstantinidis and I'm a research scientist at Nokia and Bell Labs Cambridge in UK. I will present our work on improving online meetings experience that was done in collaboration with my colleagues at Bell Labs and Bonas Ensiero from University of Calgary. Today, the work ecosystem has changed. It is now transforming patterns of communication between teams and individuals located at distance. While working remotely is not new, the current COVID-19 situation has turned teams or even entire organizations to a completely new remote-first work environment. To support this change, the work environment needs new tools. Tools that support human connection and foster social bonding. Tools that capture certain subtle cues of communication, which may or may not be present in the current ones, but could hinder our experiences, particularly during online meetings, if not supported. But don't get me wrong, there are great tools out there that we all use on a daily basis, like Microsoft Teams, Skype, Zoom, or Slido. And these tools facilitate our online communication and collaboration, particularly during meetings. While these tools provide several technological features through video, audio, and textual support, yet there are some elements that remain missing in the design space that would allow attendees to feel more connected and engaged during their online meetings. And this is exactly what our work tries to do. We propose MeetQs to support our online meetings experience. MeetQs is an interactive platform which allows attendees to engage during a meeting, reflect on, and be aware of their own and their peers' experiences. It creates back channels of communication that aim to augment our online interactions and experiences during meetings. It consists of a client-side application and a backend server-side component. The client-side application is a web-based app that works alongside a video conferencing tool called WebEx, but it can be easily integrated with any other online tool and provides a set of interactive and visual features to help people be engaged and reflect during their online meetings. The backend consists of two servers that serves the application content, record the meeting, process it, and generate analytics. MeetQ's client-side application was designed in such a way to support reflection, engagement, and awareness. We took pointers from previous works on personal visualization and casual interaction, and we made several versions of it that we tested and refined iteratively. During an online meeting, attendees can tag what's being said with a click of a button, either expressing an agreement or requesting a clarification. They can also leave comments, which is a popular feature in this kind of applications. And based on the crowdsourced interactions, all meeting attendees get an immediate feedback through an emoji cloud visualization that displays the mood of the meeting. Once the meeting is over, our backend processes the audio recording and produces audio snippets that are generated based on the crowdsourced annotations. And these snippets could serve as memorable moments to summarize a meeting. To evaluate our system, we conducted a user study with 5 real-world meetings. We looked at seminar-like meetings and recurring team ones, and in total 55 people attended those meetings. We interviewed 8 of them, and we investigated qualitatively whether MeetQ's user interface features had any effect on people's experiences during meetings. The interviews consisted of a set of open-ended questions that helped us probe our participant experiences using MeetQ. We transcribed the interview responses and conducted a thematic analysis, and we extracted 4 high-level themes that concern self-expression, visual engagement, intervention, and sense-making and behavioral change. First, the casual interactions through tagging and commenting played a major role in engaging our participants. For example, one participant mentioned that there is a hint of informality that allows you to open up more. These findings suggest the value of casual interaction and the visual metaphors used in making people feel more comfortable to contribute during their online meetings. The second prominent theme concerned how our participants used the visual features to assess each other's reactions, thoughts, and feelings during a meeting. For example, another participant found it useful to know what other people think, and especially what they tag. This suggests that our tool created an additional channel of communication that allowed participants to get immediate feedback of how others react as the meeting unfolded. The third theme is about how our tool allowed our participants to think about changing their attitude towards others. In a sense, it provided the means to identify when they could intervene through the changes in the emoji cloud visualization. But in the end, it was entirely up to them to try to change the course of the meeting. Finally, participants praised the summary page features that allow them to recall and recollect. In particular, the audio snippets allowed them to play back points during the meeting that were unclear or an argument was raised. To sum up, we proposed a new interactive platform to augment our online meetings experience. In MeetQueues, we introduced features that allowed participants to react on what's being said in real time and get an immediate feedback of the online room atmosphere. These features allowed our participants to open up more and reflect on each other's reactions and thoughts. Additionally, they encouraged them to take a step further by trying to change the course of a meeting through interventions. Finally, MeetQueues also served as a post-meeting reflection tool in which participants use it to make sense of their past meetings and get the gist of the most memorable moments. And with that, I would like to end my talk and invite questions. Thank you.
That was great, like very, very timely. We all need that right now. So thank you so much. Until we wait for a question, I will start with asking, did you start that before or after the pandemic? And yeah, go ahead.
Well, that's a great question. So actually, that work started more than a year ago.
Okay.
I guess right now it's very timely. So we all need this kind of tools to push forward. So while we are apart, we need to feel together, right? So we need to turn our physical, we need to rethink about the meetings experience. So,
so when will MeetQueues be available to?
Actually, it's a platform that we're currently using in our organization, and I can post like more details about our stuff. Yeah.
Mm-hmm. Okay, so let me ask another content-related question. So you reported what participants cared about and all of the feedback that you got, but did you actually experience that you changed the way you interact in a meeting based on the cues you get?
Paul, you want to take that?
Sure, I can go and answer that. So I would say that when I was using it, it's up to me because like when I start seeing that people, for example, become more yellow or become more like the thinking emoji, then like say if I was facilitating or if I was the one presenting, then I could maybe stop the presentation there and just say, if anybody is unclear, I can repeat myself, right? So there is like that kind of change that can happen. But when I was doing the study, there's some interesting ideas, like say, maybe they're not exactly the one who are presenting, but maybe they're the groups. Maybe they're like more senior people in the group. And when they start saying that people are maybe a little bit more questioning, then maybe they won't change the meeting right there and then, but in the later on, like as it will be some form of feedback to say, maybe we should change this part of the meeting because people aren't perceptive, things like that.
Yeah. I have one more question coming in from Discord. If you were to add one more button to the interface, what do you think would be the best addition?
Well, I guess, well, I mean, there are many other things to explore in future research, but on the top of my head now, I could think of something more like, well, I don't have an answer right now. Paul, do you have any idea on like what other visualizations or other like buttons we?
Borrowing from Zoom, I mean, they have like that congratulations type or type of a button. So it's kind of like maybe at the end of the session or the meeting, then people can clap or something like that. But
yeah, just something to give more connection to people while being not physically together in the meeting, I guess.
Yeah. Okay, Bon, Marius, thank you so much. There are more questions on Discord, but thank you so much for this presentation. And let's move on to the presentation by Laura, and it's DebateViz, Visualizing Political Debates for Non-Expert Users.
Political debates are a rare opportunity for voters to learn valuable information about candidates, such as their stances on important issues and their behavior towards their peers. However, because debates are long and dense, many people do not have the opportunity to closely analyze the trove of information included in every debate. Text visualization tools have been created to help experts in fields such as linguistics and communications explore transcripts efficiently, but the same techniques have not been translated into tools built for casual users, or people without experience navigating and extracting meaning from large bodies of text. Debate transcript visualizations for casual users are often static and explanatory, and are not connected directly to the source text, unlike more sophisticated visualization systems built for experts. To address this gap, we conducted a design study and interdisciplinary collaboration among computer scientists, journalists, and political scientists, resulting in a novel task analysis focused on casual users and the creation of DebateViz, an interactive tool for visualizing political debates for casual, non-expert users. I will now go through the 3 iterative design phases that we used to construct DebateViz, and then explain the final design in greater detail. The first iterative design phase began with informal discussion about debates with our political science and journalism collaborators. We constructed an initial task analysis for 3 domain goals. The overview domain goal reflects users who do not have a specific interest in candidates or topics and want to explore the debate at large. A concrete example of this domain goal is what did the candidates talk about in the last debate? A user with the speaker-focused domain goal is interested in the behavior of a specific candidate or range of candidates. For example, who did Bernie Sanders attack in the first debate? And finally, a user with the topic-focused domain goal wants to know what has been said about a specific topic or range of topics, regardless of speaker. For example, what did the candidates have to say about healthcare in the debate? In phase 1, we built our first pipeline for extracting data from raw debate transcripts. We extracted 2 types of data: topic labels and speaker interactions. We use a topic dictionary to assign topic labels to each utterance in a debate. The topic dictionary approach requires more manual effort than unsupervised or supervised topic modeling, but also produces more comprehensible results. Additionally, the topics discussed in a debate often reflect news stories and recent campaign developments, so a manual topic dictionary approach is well suited for this problem. For example, let's look at an utterance from Senator Bernie Sanders in the 10th Democratic debate on February 25th, 2020.
What the American people want, by the way, and a lot of the issues we'll be discussing tonight are issues I raised 4 years ago. Raising the minimum wage to a living wage, $15 an hour, making public colleges and universities tuition free, and finally doing what every other major country on earth does, guaranteeing health care to all people as a human right through a Medicare for all single-payer system.
The topic dictionary assigns Sanders' utterance to the topic labels healthcare, economy, and education. The second data attribute we extract from raw transcripts is speaker interactions. Debates provide a rare opportunity for candidates to interact face-to-face. lesser-known candidates can attack their more successful opponents to try to draw attention to their campaigns or form alliances by agreeing with others on stage. For example, let's look at an interaction between Senator Elizabeth Warren and Mayor Mike Bloomberg in the 10th Democratic debate.
I don't care how much money Mayor Bloomberg has. The core of the Democratic Party will never trust him. He has not earned their trust. I will. And the fact that he cannot earn the trust of the core of the Democratic Party means he is the riskiest candidate standing on this stage. All right, Senator.
We define a speaker interaction as a direct reference by name to another candidate in the debate. Speaker interactions fall into one of four categories: attack, agree, neutral reference, or defense. Phase 2 of our iterative development coincided with the start of the 2020 U.S. Democratic primary debate cycle. After making changes to the interface to account for 10 candidates on stage at a time, we visualized the first 2 debates with DebateViz and conducted usability testing with people who had not watched the debates live. We found that participants wanted to be able to bookmark and share specific moments within a debate to launch further discussion with friends and coworkers. So we updated the task analysis to include a share domain goal and added a custom URL feature to allow users to share debate moments directly. We also found that participants were interested in looking at audience reactions to each candidate, so we added audience interactions such as applause, laughter, and booing into our data abstraction and pipeline. To begin Phase 3, we recruited 5 people to participate in one-on-one semi-structured interviews about DebateViz. Because our evaluation interviews lasted longer than previous usability testing, we were able to observe users as they adjusted to the interface and began asking deeper questions about the content of the debate. This led us to realize that our task analysis was missing one final domain goal, which lay at the intersection of the previously defined speaker focus and topic focus goals. Evaluation participants frequently mentioned wanting to know what a specific speaker said about a specific topic, so we added a new domain goal to our task analysis called Topic Speaker Focus. A user with the Topic Speaker Focus domain goal wants to learn about the relationship between a given speaker and topic. A concrete example of this domain goal is what did Beto O'Rourke say about gun control after the shooting in El Paso? Participants in the Phase 3 evaluation appreciated the inclusion of audience interaction data. 2 participants even used audience interactions as a mechanism for exploring the debate by investigating every instance of audience laughter. However, most participants had trouble understanding the chord diagram in the Phase 3 design, even after using the interface for a significant amount of time. In the final design, we simplified this component by using a more straightforward node link diagram. I will now go through the final design that we reached after 3 phases of iterative development. The DebateViz interface has 3 linked views: an annotated transcript, an interactions graph, and a timeline. The annotated transcript includes every word said in the debate, along with annotations highlighting interesting aspects of each statement, such as mentions of important topics and mentions of other speakers. The transcript is useful for close reading, but is not efficient for exploration or for seeing broader trends. To encourage both of these tasks, the timeline visualization shows a high-level view of the entire debate at a glance. The user can click on any mark in the timeline representing topic mentions, speaker mentions, and audience interactions to navigate to a specific moment in the transcript. The interactions graph provides another way for users to discover trends in the transcript. A node link diagram connects speakers according to the number of times they are mentioned by their peers, providing a glimpse into the complex on-stage dynamics that often play out too quickly to keep track of when watching a debate live. The interactions diagram can also be used to investigate how candidates interact with the issues being discussed on stage. For example, which candidates devote most of their time to discussing gun control, or which candidates dominate discussions about healthcare. Linked views for close and distant reading allow DebateViz users to quickly and easily explore dense debate transcripts, look up what candidates said about topics of interest, and examine each other. The task analysis and visualization framework developed over the course of our design study will help developers create text visualizations in the future that are accessible to all users, regardless of background, without sacrificing explorability and efficiency.
Great, thank you, Laura. Another very timely and great application here. So we have some questions coming in from Discord. First, how scalable could this tool with interface, for instance, for parliamentary discussion debates where the length of the discussion and speakers are usually of an increased order? So longer debates than presidential debates.
Yeah, that's a great question. One thing that's interesting in that question is that there's many ways in which this type of visualization has to scale, right? It has to be scalable in terms of the number of topics that are discussed, the number of speakers that are on stage, and the absolute length of the debate. And so I would say that the system, I think, is fairly scalable in all three of those dimensions. First of all, for the number of speakers in the debate, we actually were able to use DebateViz to visualize the Democratic primary debates of this election cycle. And at the max, I think we had 12 candidates on stage speaking, essentially at the same time. So we were able to visualize 12 candidates. So it's fairly scalable in that sense. And then in terms of the absolute length of the debate, I think it would, we haven't tried longer than the average. On average, the presidential debates are around 1.5 hours to 2 hours. So we haven't tried anything longer than that, but I can't see any reasons why that wouldn't be just as functional. So yeah, great question though.
Yeah, great, thank you. So there are more questions coming in on Discord. We can move the discussion there because in the interest of time, I'll move into the last talk. Thank you, Laura.
Thank you.
So our last talk is by Bruni, and it's entitled ClaimViz, Visual Analytics for Identifying and Verifying Factual Claims. Go ahead.
Hello, I am MD Mainuddin Roni. Today I am going to present our visual analytics systems ClaimViz. Determining the veracity of a factual claim made by public figures has become a common task for journalists in newsroom. However, fact-checkers face critical challenges as they swipe through a large amount of text to find out claims that are checkworthy. Although there are some computational methods to identify factual claims automatically, there is a knowledge gap of designing an effective system for the users to take advantage of computational methods. In our work, we aim to reduce this gap. So our goal is to design a system where we can combine natural language processing with visualization techniques that could support the users in spotting and verifying claims. In order to do so, we conducted a design study with professional fact-checkers to understand their challenges and requirements. Based on this, we designed a visual analytics system combining natural language processing and interactive visualization techniques to explore and evaluate the potentially checkworthy claims in a large transcript. After that, we evaluated the system with professional fact-checkers to prove its efficacy. For requirement gathering, we followed the visualization design study method and interviewed 3 professional fact-checkers from PolitiFact and Duke Reporters Lab. The interview was open-ended in nature and was run in a focus group setting so that it could open up a diverse range of issues and possible solutions. The participants provided important insights into their current work practices and challenges. For example, lack of ability for humans to provide input and absence of contextual information. Our conversation with domain experts revealed several important analytical tasks, including to get a visual overview of how checkworthy claims are distributed across a transcript so that they can quickly spot the interesting claims, finding all claims made by a specific speaker of interest, and finding relevant evidence for a given claim to verify. Our system applies several text analysis techniques on the transcribed document and then visualizes the results to the user. We adopted a deep learning model to predict the checkworthiness of each sentence. In addition to the prediction, the model also gives us information about words that contribute most to the checkworthiness of a sentence. Our manual exploration revealed that there are 4 prominent types of claim exist in a script. We devised a rule-based classification technique that categorizes a claim into one of the 4 types. There are some other text analysis techniques we applied on the transcript, for example, topics, sentiment, and evidence mining. Now we are going to show the demo of our system.
In this demo, we present how ClaimViz can be used in a debate transcript. ClaimViz has three main panels. The left panel contains the topic and speaker information. Topics are determined automatically using an algorithm named by-term topic modeling and are represented by top keywords of that topic. Users can filter the transcript based on topic keywords as well as speakers. Finally, the user can search for keywords using the search box at the top. The middle panel is called Minimap, which provides a visual overview of the transcript so that the fact checker can locate check-worthy claims based on the claim scores about specific topics. The small rectangles in the minimap represent sentences in the transcript. When a rectangle is hovered, the corresponding sentence becomes visible as a tooltip. There are two types of columns in the minimap. The first type represents topic, and for each topic column, the system shows the statements that fall under that particular topic. The color of these rectangles matches the topic color. When the user makes any selection in the left view, the relevant rectangles under the topic columns get highlighted. Another type of column represents the claim type for each statement. Here, the color saturation of a rectangle depicts the checkworthiness of the corresponding sentence, where the darker tone indicates the sentence is highly checkworthy. The panel also has a filtering option of the transcript based on the claim score. The right panel shows the transcript of the debate in the chronological order. Along with the speaker's attribution, it shows the sentiment and checkworthiness score of the corresponding statement. To help the user understand why the system predicts a sentence as highly claim checkworthy, it highlights the words that contributed towards higher claim scores. It also has a bookmark option, and whenever the user clicks on this button, the corresponding sentence is added to the bookmark section. Now, let's imagine a fact-checking scenario. Suppose a fact-checker John wants to find out all the checkworthy claims made by Bernie Sanders on the issue healthcare. John started by selecting Sanders from the speaker list, and then he selected the word care from the topic list. In response, ClaimViz highlighted all the sentences from Sanders related to the issue care. To find the most checkworthy claims, John then decided to use the slider, and as a result, John can now see all the highly checkworthy claims. Then he decided to quickly browse through the statements by clicking on the rectangles from the minimap, and after clicking, he felt that this particular sentence is indeed highly checkworthy. So he decided to bookmark it for the future review. Finally, in order to verify the claim, John decided to click on the search icon. As a result, the interface finds relevant documents to this claim and highlights the sentences that may provide evidence for this claim.
To test the efficacy of ClaimViz, we ran case studies with 4 domain experts. Through the studies, we wanted to understand, does ClaimViz help target users in finding and verifying claims effectively? Which visualization features worked and did not work? What can we learn from their feedback to improve the system? The participants have extensive amount of fact-checking experience ranging from 1 to 4 years. This study is designed on 2 debate transcripts. In the study, the participant performed 2 types of tasks. 4 target criteria tasks where they would have to find checkworthy claims about some specific topics or speakers or both, and an exploratory task with a different transcript where they would have to find 5 most checkworthy claims according to their own interests. According to the result analysis, all participants found the ClaimViz interface to be effective in identifying checkworthy claims. In particular, they mostly agreed that showing the topic and claim score of each sentence in the minimap is useful. All participants liked the interactive features of faceted exploration by topics and speakers. Although ClaimViz mostly met the identified task requirements, there were some concerns from participants. Some participants thought people who are not familiar with technology may take some time to understand how it works. Moreover, while all participants agreed that the filtering by claim score was helpful, 2 of them did not find the word highlighting feature equally helpful. Some participants suggested additional features to enhance the fact-checking process. For example, one participant suggested to add sentiment distribution for the speakers. ClaimViz supports the user to interactively filter sentences in a long transcript to find the highly checkworthy claims, followed by verifying the claims by finding potential evidence that may support or oppose the claim. But there are some limitations. Our current system only supports conversational scripts. In the future, we will extend our system for supporting fact-checking with other corpora, for example, social media text. Moreover, the verification component of the system identifies similar sentences using sentence similarity. We want to enrich it with further linguistic analysis such as stance detection and argument mining. We have provided the live system link here. Thanks for listening. If you have any question, feel free to ask.
Thanks, Ronnie. Another very important topic. We have some people typing, but until we get some questions on Discord or YouTube, I have a couple of questions. First, often when you have these sort of debates, you have people referring to the same concept by different words. So, for example, people would say Obamacare versus universal health care and so on. Have you thought about methods on how to combine all of these aspects so that you get claims and do some fact checking on concepts that might have this different names but are indeed the same thing?
Yeah, that's a nice question. It's also a concern from the professional fact checkers that there are many topics in the debate that may have span over different topics, but they can be merged together. So we haven't focused on this issue so far, but in our future, we are planning to explore this problem also, where we can merge the similar type of topics together and help the fact checkers to explore these things.
Okay, great. I'm looking forward to that. Thank you.
Welcome.
So, if there are any more questions, please take them to Discord. Now I'd like to thank all the presenters again, all the viewers and everyone contributing to the discussion on Discord and YouTube. With that, I would like to close the session and thank everyone. Enjoy the rest of the conference.
Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract the vortex boundary, however, varies spatially. To detect vortices without manual thresholding, we utilize supervised deep learning. For the regression, we evaluate 3 recent network architectures. The resulting networks are able to detect vortices that grow in size due to diffusion, despite their angular momentum becoming smaller.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of two different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to three major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
The mixture graph is a data structure for compressing, rendering, and querying segmented volumes. Biomedical segmentations have evolved from mere annotations to first-class modalities. The mixture graph stores the computations required to render such nominal data directly on the GPU, including pre-filtering and lighting. Segment distributions can be queried efficiently using regions of interest.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Visualizations are about visual patterns, but there's more, much more. We show the connections between more than 100 arguments on why visualization works. And don't forget to check out our website.
We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
Traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
Hey everyone, I'm Junhan Zhao, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Persevere, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhen Dai, Dr. Panpan Xu, and Dr. Liu Ren.
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets, and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method. For example, visualization of multivariate particles and visualization
to interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
Given a dimensionality reduction scatter plot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
We propose a multi-perspective simultaneous embedding (MPSE) algorithm for visualizing high-dimensional data based on multiple pairwise distances between the data points. MPSE computes positions for the points in 3D and provides different views into the data by means of 2D projections that preserve each of the given distance matrices. MPSE works on abstract data as well as graphs.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, They hide important factors such as inner-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
The transmission of pathogens such as bacteria and viruses is an acute problem in hospitals around the world. Infection control experts need to monitor infections and determine transmission pathways. We developed a novel visual analytics system for the exploration of disease outbreaks. It combines several interactive views and a tracing interaction that allows to detect pathogen transmissions.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
We present a framework for the visual exploration of spine simulation data. We show the force distribution on spinal discs, enable assessments of imbalances, and reveal impact vectors that were not accessible before. This is a novel direction in medical visualization, and we hope that it might bridge the gap between biomechanical research and clinical application.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Hi everyone, I hope you're doing well. I'm Heikyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, Bluff visualizes the activation pathways of both benign inputs and attacked inputs. That is, Bluff finds and visualizes the most activated pathways given benign and attacked input data. Bluff also visualizes the most inhibited paths by the attack to uncover where the attack is blocking the signals to the benign path. Also, Bluff visualizes the most excited paths by the attack to uncover where the attack stimulates to induce the activation pathways going towards wrong directions. The Bluff interface tightly integrates three coordinate views. It consists of control sidebar, graph summary view, and detail view. Here, a user inspects why a deep learning model misclassifies adversarial giant panda images crafted by the projected gradient descent attack as armadillo. In the main graph summary view, we visualize the activation pathways of benign and attacked input data. Here, each vertex represents a neuron. When hovering over a neuron, Bluff shows the detailed information of the neuron. The detailed view for a neuron shows a feature visualization and example data that visualize what feature the neuron is detecting. For example, for giant panda images, this neuron looks for face of animals that have white furs and dark eyes. Feature visualization is a synthesized image that maximizes the corresponding neuron's activation. Dataset examples are patches of images from the training data that highly activate the corresponding neurons. We also show how the neuron's median activation would change according to different attack strengths. Here in the graph summary view, the neurons are represented with different colors based on their roles. The green nodes are the most important neurons only for the original class, giant panda, which means They are highly activated by benign giant panda images. The blue nodes are important neurons only for the target class, armadillo. The orange nodes are the most important neurons for both original and target classes, giant panda and armadillo. The red nodes are the neurons that are highly activated by only successfully attacked images. These neurons are exploited by the attack to induce the incorrect prediction. By exploring the activation pathways, PGD successfully perturbed pixels to induce the brown bird features, an appearance more likely shared by an armadillo than a panda. Both armadillo and brown birds have small, roundish, and brown bodies. The brown bird neuron then contributes to the armadillo misclassification by activating
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets, and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method, for example, visualization of multivariate particles, and visualization
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
Different sampling strategies have different performances in preserving features, but which one is the best? In this paper, we selected 7 sampling strategies along with 8 representative datasets and 3 important visual factors. We formulated 4 hypotheses and conducted a user study with 100 participants. For the derived insights, please refer to our paper.